Okay, well, thank you, everyone who's joined in for this session on using generative design and digital twins to improve occupant well-being. First, a little bit about myself. So you can find me on Twitter and LinkedIn via Kean W. That's the easiest way to get me. There's also my blog at keanw.com. So as Laurie said, I've been with Autodesk. I started at Autodesk 25 years ago in 1995. I spent my first 17 years of the company in our developer network team, so focused on helping external software developers be more effective with our technology. I have a computer science background, so I've always been involved in programming at some level in my career at Autodesk. From 2012 to 2016, I moved into the AutoCAD team as a software architect responsible for some AutoCAD-based verticals. And then from 2016 onwards, I've been in the research team, and my focus there has really been on helping build Project Dasher, which we'll talk more about, using web technology, and then exploring the use of generative design technology for different problems. So you can also see that on the very right hand side over here, I've been around the world as well with Autodesk. I started in the UK, hence the accent, and then moved to Switzerland in '98, then California in 2000. I moved to Bangalore, India in 2003, and then since 2006, I've been back in Switzerland, and I'm fairly well settled at this stage, I think. And then since 2006, I started keanw.com, what's at keanw.com now, but it's called 3D Interface. It started off as being a blog that was focused really on software developers working with AutoCAD, but since then it's evolved as my career has evolved as well. So these days I do spend quite a lot of time talking about using Forge, but also talking about generative design. So if you want to dig into anything related to today's presentation, you'll find a lot of useful content there, I hope. So the two areas that I really want to talk about fit into two parts of this overall visualization, and this is so the first area is over here on the Internet of Things. So this is talking about monitoring performance of built designs, of whether it's buildings or bridges, and then eventually feeding that data back into the generative design process, which takes data that's quantitative and qualitative in nature, but also data based on building on the actual real world performance that's captured using sensors, and essentially generates a number of different solutions that can then be evaluated based on various metrics. So I'm involved, I guess you could say I'm involved in these two areas that are highlighted in yellow there. So this is the classic generative design loop, and then this is the monitoring aspect. At the moment, they're not highly connected. We tend to work on digital twin related projects, which I'll talk about first. And then we also work on generative design projects, but increasingly these two areas will be connected as the data that we capture on performance is going to feed into the generative process. But we'll see this slide again towards the end of the presentation, just to summarize. So our first foray into a digital twin, I mean, it wasn't called a digital twin at the time. It wasn't even called the Internet of Things at the time. This was at the end of 2009, beginning of 2010. We first built the desktop version of Dasher, which essentially allowed us to take time series data from that had been collected from sensors and stored in a database, and integrate that into a 3D context. So at the time, we were taking data through IFC and building, importing that into a desktop application. When I came into Autodesk, when I came into research, my first job was essentially to take the work that had been done on this desktop tool and create a web-based version, which you can find at dasher360.com. It's still an ongoing research project, but it's we've made some important progress with it. So this is a view of what you will see at dasher360.com. Though this is a project that quite early on we realized the potential for being able to take large amounts of data and integrate it into 3D, This was actually a project for NASA. You can see the logo. I've blanked out the logo down in the bottom right for copyright reasons. We're not allowed to show that publicly. But essentially, this was a research center of theirs in California, where we instrumented very heavily the building. And this is just the data that we can see from the second floor. I don't know how well it comes across with the video, but what you should be seeing is quite significant kind of rippling and temperature variation across the second floor of this building. When we showed it to people at NASA, they had a couple of things that they pointed out initially. So first of all, they noticed that this area here was had a different temperature profile, and I said, well, that's normal. It's where we store our servers. It's the server room, so they are cooled greater than the rest of the floor. But then they also noticed this room down in this corner here. And on reflection, they will very quickly said, oh, wow, that's where we're doing the glazing study. Or we've been doing a glazing study for a couple of years, but we haven't had time to crunch the data on it. So it was really only at this time when they saw the IoT data contextualized in 3D that they had this real aha moment regarding the possibilities related to this particular technology. So I think that was really for us as well, a moment where we said, maybe we're onto something here and there is some value in this. I will also mention that a lot of our driving force behind the original Dasher project and to a large extent today is around optimizing the use of buildings and relates this to sustainability. How can we improve the efficiency of buildings, and that will in turn help the planet and help us reduce the amount of energy that is used to keep buildings running. So a second interesting project that we embarked upon was with Schneider Electric, and this was a building of theirs in the south of France where they'd integrated some new sensors of theirs, which actually were able to track occupancy. So you can see these sort of purple or pink or purple Playmobil people that are showing up. So these sensors allowed us to really, understand exactly where in the building people were spending time, but we could then correlate that with CO2 data or temperature data or humidity, it doesn't matter. But in this case, it was most interesting to take a look at the CO2 data because we could very quickly see, well, there were spikes in the data, and we could then slow it down, dig into the data at different levels, and even pull up individual sensors and scroll out or zoom out on the data and say, well, how often are we seeing spikes of this magnitude, and what sort of things would we need to change in the building system in order to prevent these situations where people inside a conference room are, not able to get the oxygen they need. So this was another interesting aspect of being able to take data and correlating it. So we're taking multiple types of data and overlaying it, not just one stream. Here we have occupancy and CO2. So the next large shift in the project related to our need or desire to support infrastructure data as well. So we have a big project that we embarked upon with which I'll talk about in a little while. But this was the prototype that we built in our Pier 9 office in San Francisco. So they have a raised footbridge that connects two parts of the building. We went in and put in accelerometers, strain gauges. We hooked into the CCTV cameras that were on the bridge as well. And that allowed us to explore, again, data that relates to infrastructure, not just to buildings. So this is a 3D view looking across this particular footbridge. Here we're taking the data from the bridge, which you can see, in the graph below, but correlating it with the CCTV footage of somebody walking across the bridge. So this allowed us to understand how the bridge was performing when people used it. We could see how many people were on the bridge, what they were doing more or less. But it still involved the need for somebody to take a look at the data and make sense of the camera footage. So the next step for us was really to go beyond just looking at camera footage and say, well, what can we do next? Well, how can we make this more valuable? And it's at that point we started to integrate computer vision into the pipeline. So here you can see just detecting the overall shapes and positions of people on the bridge. But then we took it a step further and started to do, frame by frame skeleton extraction so that we could then really understand how many people were walking across a bridge and what they were doing. Sorry, there's a little bit of noise on the phone, and I think somebody must be unmuted. Tina, are you able to take care of that? Otherwise, I'll just carry on. All right, thank you. All right, so one of the things, once we were able to extract this skeleton data, not just in in a 2D plane, but we were able to extract it in 3D, we could then start to play that back essentially inside Dasher to show people moving through space. And this all related to a project, as I mentioned earlier, for a startup in Amsterdam called MX3D, who've been building the world's, and I have to get this right, the world's first 3D printed steel bridge. So there are other 3D printed bridges which are made out of concrete, but in this case they had a vision of being able to take robots and have them weld their way across a canal in Amsterdam. So here we have this was an image that they had early on to sort of show the vision. Clearly it wasn't viable for them to actually have welding robots in a public space without some protection for people's eyes. So realistically, the vision shifted to be done this was a warehouse that they occupied at the time in NSDM Wharf in Amsterdam. Eventually, the vision ended up being more a bit like this. It wasn't robots welding their way across to meet in the center, but it was nonetheless an important piece of research and very interesting in the sense that this is a whole new material that's being used to build something out of. It's not necessarily new material, but it does have new properties when it's been, built up layer by layer in this way via a welding process. So of course it was important to understand how this new bridge would perform, and not just perform under normal conditions, but how would it perform in midsummer? How would it perform in the depth of winter when it's covered in snow? We went to the bridge and did some jumping up and down on it. This was for fun. This is a bit of drone footage that we captured. It had actually already been tested with I think 10 or 20 tons of water just to really make sure it could support that weight before we did this. But it was a little bit of fun to try it, to test it out. But really the idea is that we would integrate a network of sensors, including accelerometers and strain gauges, but also temperature sensors, etc., in order to really understand how this new piece of smart infrastructure works in reality. So we also had camera footage in this. This is from Dutch Design Week in 2018, where we had a couple of cameras set up on either side of the bridge, and it allowed us to with this kind of view, we could take a look at the 3D skeleton data that we had and really understand how it related to the video footage, and to make sure that we had some correlation. So this was just a sort of more like a debug view. Ultimately, the idea is to throw away the video footage, and it really anonymizes the data. This bridge is going to be placed in the red light district of Amsterdam, so it's clearly highly sensitive in terms of capturing data about its surroundings. We need to make sure that everything is completely anonymized, to protect people's privacy. So here is the kind of the next step of what we wanted to be able to do, was again this idea of correlation. So here we're showing people walking across the bridge, but also mapping data around the bridge's performance. In this case, it's acceleration data, which probably doesn't make sense to display as a field, but it was the data that was most useful, or created the prettiest pictures at the time. We're still working on this project in order to take calibrated data and be able to really correlate the streams together in a visualization such as this. So excuse me. So another project that we've been working on, and still to some degree working on today, relates to the Nest building in a suburb of Zurich. So this is really a showcase for digital fabrication techniques. It's a highly modular building which is really testing out different concepts such as urban mining, material passports, circular economy, lots of different types of digital fabrication, whether it's with wood, with concrete, etc. So it was a really very interesting project to be involved in, especially as they had data from upwards of 2,000 sensors inside the building that we could just access and integrate as needed into our model. So if you go across to dasher360.com and click on demo, you will get access to this same view. In fact, what I've done here is I've just recorded a view of what's known as kiosk mode. If you go down into the bottom left-hand corner here and click on this button, it will essentially run a scripted demo of stepping through different features, slightly different each time because it does things a bit randomly. But it allows you to really get a sense of how Dasher works. So if you want to take a look at it, go ahead and you can go across to dasher360.com and click on demo and then click on kiosk mode and see it running for yourself. So the sort of data that we're able to see with this, and this is another view animating, again, in this case, temperature data. So we can see here that we're sort of using Dasher's capability of contextualizing data to create some surface shading for each of the rooms across the first floor of the Nest building. In this case, as I said, it's temperature data, but you can really pull up the data on pretty much anything. And I think this is where things start to get very interesting as we move into a post-COVID world as well, because at the moment, I mean, Autodesk is still not back in our offices, so our focus has really not been on this. But as we start to go into our offices, we will start to think about what data we can capture in order to monitor how the space is being used, such as taking sensor data perhaps related to temperature, perhaps related to other things as well, occupancy, etc. And then how do we map that into a usable form where we can start to assess things like risk related to viral infection. Here was a project that we did for a company called Kingspan in Ireland, and this is their Icon headquarters. So here, we're able to take a look through the excuse me, use kind of an X-ray mode to take a look through the walls and understand, well, what does the mechanical infrastructure look like inside the building, which allows us, again, to sort of get more information about how the building's performing and relate that to what we're seeing in the IoT data as well. So understanding HVAC and integrating data from HVAC into a digital twin is going to be increasingly valuable moving forward. We also, at the Icon building, integrated off the first capability, and you can only see one skeleton here, but there you have a skeleton integrated as well into the office environment, so we could start to understand people flows through the space. You can easily imagine using these kind of computer vision techniques that we could tell when people are performing actions or have behaviors that could put people at risk as well, whether it's excessive touching of surfaces, maybe even sneezing, lots of things that could potentially be understood and monitored and allow us to better control the risk of viral infection. So that's what we've been doing with digital twins. Once again, this is this view again. We've been focused on this monitor side of things. So let's take a little look into some of the activities we've been doing on the generative design side, and hopefully you'll see how these things will connect in due course. So this is the first major generative design project Autodesk did in the AEC space, and it's probably one that many of you are familiar with. This is our Mars office in Toronto, where essentially we went in and wanted to use a generative process to design the layout of this new office. And so we went in and established a number of metrics, some that were based on survey data from humans, such as who people prefer to be next to, what sort of work style they have, but also taking other data, other constraints from HR in terms of which teams were what sizes of teams we had and how we could fit those into a space. We also had metrics that allowed us to assess human comfort. So things such as daylight, views to the outside. We also wanted to minimize the amount of walking that people had to do to get from their desks to various amenities, whether it's to the elevators, to the coffee area, to the restrooms, etc. So we had various metrics. We also wanted to increase buzz, which is something I'll be talking more about. So buzz is this idea of interconnectivity, but this idea that as people walk through the space, we wanted to encourage common walkways so people would have these serendipitous encounters and water cooler conversations where they'd chat about projects and things, and to increase the interactivity inside the office. So we had these various metrics. Now, once you have these metrics in place, you can use them to evaluate numerically each of the different designs that you run through this process. So essentially you have a parametric model, which we can see down in the left-hand side here, where there has a number of inputs, and then each one of those inputs will generate, or each time you vary the inputs, it'll generate a excuse me, a different design, which can be assessed based on the various metrics on the other side here. And then the optimization process is going to do an intelligent search of the design space, because you couldn't really do a systematic search, because with so many different input variables, it would essentially take forever. So it does uses an optimization mechanism to take the input variables, tweak them slightly, measure the effect on the outputs, and then gradually hone in on the more interesting solutions. So here we've done a random run which has thousands of different solutions, but typically you don't need that because you'll be doing a much more intelligent search of the space. And eventually a particular solution was selected in order to be further refined. And this is that solution. So this is the overall project that we had originally for designing the Mars office. Where I got involved was to take that the work that had been done on what we called Project Discover, and I was involved in helping create a version that could be shared publicly. And this was as part of what we called Project Rediscover. And you can go to autode.sk/Mars-graph and download the Dynamo graph that you can try for yourself that essentially replicates this process. There are a few differences. We haven't included employee data related to people's work preferences and their teams, etc., because of course that's sensitive. But largely it works in a very similar way to the original project. So when we first, obviously the world was very different when we designed the Mars office in Toronto. As we went into confinement and the world was starting to look very different, we started to, well, again, this is another visualization of that same office. This is just us of the same layout, but us visualizing data in a slightly different way. But when we went into the kind of COVID confinement period, you could say, we started to think about things differently and to say, well, what is it that needs to change with this kind of mechanism in order to think about returning to work after confinement, and what the offices will start to look at. So obviously we were saying, well, clearly we're going to have more spacing, physical spacing, between people. Buzz is no longer a good thing. We want to actually optimize the space so that people are not bumping into each other and potentially spreading the virus. So, how do we optimize the space in order to do that? But, maybe daylight is something we want to encourage even further, with in the future, in order to, because there are obviously studies that are coming out that say that daylight is a very good thing for killing the virus as well. It's important to note that as we've been going through this process and this thinking, we still don't know everything there is to know about COVID-19. We're getting information every day about the questions, some of the assumptions that we've been making. So a lot of the things that I'm going to be talking about in the next few slides are very much a work in progress. But what we are finding is that generative design as a mechanism is very tolerant of these changes. So as we learn more, we can modify the metrics. We can build in new metrics. We can start to expand the system in order to take into account these new learnings. So it's a very flexible technology to apply to this kind of problem. And I think there is definitely some potential for using it further moving forward. So more specifically about the sort of metrics we have been starting to put in place, we're using a Dynamo package that we used originally, or built originally as part of Project Rediscover, called the Space Analysis package. Now, space analysis allows us to do things like pathfinding. It also allows us to do visibility and acoustic analysis, but we've been able to use that same package to assess these three different areas, or these implement these new metrics essentially. On the left-hand side here, the first one related to desk proximity, and this essentially allowed, assuming that you have some occupied desks close to each other, we're able to say, well, this is a hotspot. If you had a third desk occupied as well, this would be an even hotter hotspot, let's say. So we had this idea. Oh, I should probably say that a lot of our thinking, at least at the moment, related to the post-COVID return to work, does not relate to completely redesigning desk layouts. That is something that will happen for the longer term projects. But right now, we're not even looking at changing the layout of offices. The feedback that we've had from customers is more commonly that they'd like us to be able to provide a tool that they'd like to have a tool that allows them to reactivate certain desks, but not others. So essentially, there is no space for them to store furniture. They just want to say, well, okay, these desks are the ones that we're not going to use, and how can we measure the space in such a way that tells us which desks should be turned off or not. So here we have, desk proximity is a clear one. This relates to physical and social distancing. This is an interesting one in the sense that it's not just about proximity of desks. Well, it's not looking at proximity of desks. It's looking at the pathways from people's desks to shared amenities. And this relates back to what we saw with the Mars graph around buzz, but it's kind of the opposite of that. We're looking at congestion rather than buzz. We don't want people to have only one choice of a pathway of getting from A to B. We want them to also have choice that will lead them to not having to bump into it, and to bump into each other. So that was congestion. Exposure is the third one, and this is kind of in this sense it's about how do the congested pathways affect people's desks. So here, for example, it's clear that this particular desk is very close to a congested pathway. It probably needs to be deactivated. So this is something where this particular layout is going to perform poorly because of the exposure of this desk to this pathway going through. Okay, so these are three metrics that we've put in place. We've started to assess, this is again the Toronto office with different levels of occupancy. I'm not sure how well it animates with the video stream, but here you can see over time the occupancy is increasing, and obviously it's impacting these other metrics which we want to minimize. So of course, when you have zero occupancy, these are all right at the, it's full because that's ideal for us. With zero occupants, the building is great. But as soon as you increase occupancy, it gradually turns into a sliver where these metrics that are trying to be minimized are growing effectively. So this is really, this is all done inside Dynamo. It's still early days. We're definitely interested in talking to people who have feedback about this type of exploration and would like to contribute to it. So please reach out if you feel that this is something that's of interest to you. Beyond that, it is something that in due course we expect to provide to people, whether via my blog or through other mechanisms that we have for sharing projects with the outside world.